Here we are again. We are going to start studying our own galaxy. We're going to reveal the Milky Way. So in this particular little lecture, we are going to discuss how our galaxy looks like and how stars orbit in our own galaxy. Our own galaxy, that's spilled milk. So you might remember we talked about that. On a dark night, we can't really see, especially with the naked eye, much, but we do see on a good dark night a faint band of light slicing across the sky through several constellations, including Sagittarius, Cygnus, Perseus, and Orion. Remember, we talked about Orion Nebula. We see that Orion Nebula because that is inside the disk of the galaxy, inside that pancake that we inside of which we live as, say, a grain of flour. So this band of light looks like a flowing ribbon of milk, and it looked like that to the ancient Greeks. And the word galaxy actually is echoing the Greek word for galactos, which is Greek for milk. Pretty neat, isn't it? So that's where the name is coming from. The way of the milk, basically. Now, remember, we also talked about how in the early 17th century, Galileo Galilei used his telescope to prove that the light of the Milky Way comes from a myriad of individual stars, right? Okay, so that band of light is actually millions to billions of stars. Okay, and now if we use a binocular or a really good telescope, we actually get to see some dusty gas clouds that obscure actually this kind of part, that band of light. It creates some structure, and that is due to a bunch of dust, molecular clouds where actually stars form, and those are the interstellar medium we talked about. So the true size and shape of our Milky Way galaxy are hard to guess from the way it looks in our night sky because we live inside it. And so, basically trying to determine its structure is somewhat like trying to draw a picture of your house without ever leaving your bedroom. So, obviously, this is hard, but what makes the task even more difficult is the fact that much of our galaxy's visible light is hidden from our point of view, right? So we are somewhere here, right? So us, or solar system, and you see these things, those are the dark nebulae, which are molecular clouds where stars form. So it's been actually only recently that we have had the technology to observe the galaxy in other wavelengths of light, like besides the visibles, and especially as we will reiterate in this chapter again and again, it's been through infrared observations of the sky that we realized a lot more about what's happening in our own galaxy. So what do we know about our galaxy? It definitely holds more than 100 billion stars, and it is just one among tens of billions of galaxies in the observable universe. And our galaxy is a vast spiral galaxy. Okay, you don't see any of those spiral arms in this edge-on view of our own galaxy, and again, an edge-on scheme of the Milky Way, right? Or schematic view, if you wish. Okay, so just so you get a sense of what are the elements of this stellar system in which we live. So this is the very center. It's actually very hard to measure. The center of a galaxy could be a bit different in different wavelengths. So it is a disk, and that's the edge-on view. And how big is that? Look at that. It takes basically about 100,000 light years for light to go from one edge of the disk to the other. How thick is the disk? So thickness of the disk of the galaxy, about 1,000 light years. Okay, so it takes about 1,000 years for light to travel from above the disk to below the disk. And the sun is located at about 28,000 light years, so it takes this many thousands of years for light, say, from the galactic center to reach us. Okay, and us, by us, mean the solar system, which is sun and 8 planets plus asteroids plus comets, of course, plus dwarf planets, about which we didn't talk much in this class because this is not the class we talk about the solar system. Again, there's the astronomy 120 when we talk about those things. And besides the disk and the dimensions of the disk that we mentioned, there is also an agglomeration of stars that form a spheroidal component that we call a bulge. So it's a dense region of stars that is not as flattened as the majority of the galaxy. And what also happens, in the halo, so there is a spheroidal component of the galaxy, which is much sparser in terms of things that exist in it, that we call halo, in which we find the so-called globular clusters. So, these things, again, globular clusters. We talked about the clusters of stars. We talked about those when we talked about stars, but we're going to review their importance actually in very, very, very soon. Okay, so those are really old stars mostly. Okay, so this is how the Milky Way would look like if we actually had been able to travel for at least 1,000 years at the speed of light, right? Just to be somewhere above the disk, right? So we have here a pole-on view of our galaxy, of our own Milky Way. So this is where you would be able to see the spiral arms, but of course this is just an artist's conception of how the Milky Way looks like, and we're going to talk soon about how we figured out, how the exact location of the spiral arms, the size, and what's happening in them. So again, here you see where the bulge component is, and there are globular clusters in the halo, the spheroidal component that kind of encompasses the disk, and the spiral arms where basically most of the star formation happens. So we have here the so-called emission nebulae. Where star formation happens. This is where the stellar nurseries are, like the Orion Nebula. How do the stars move in our galaxy? There are quite a few different types of motion. There are, first of all, stars in the disk, and they orbit all in the same direction. They all go in this same direction, okay? Basically, that's the disk of the galaxy that rotates around its center, around its axis of rotation, with the only little exception of the fact that they have a little bobbing up and down, okay? And they do that because of the gravity of the disk. And by disk, we mean all the stars that make up the disk. All right. And then there are orbits of stars in the bulge. Okay. So, two, we have orbits of stars in the bulge and the halo, all right, that have random orientations, and they basically right, so they go really far above and below the disk, okay, especially, right, so these are the halo stars and the red ones here, those are the bulge stars. So the bulge is not something solid, it's basically a very high dense region of stars that have these random their orbits with random orientations. Okay, so remember we talked about how the orbital motion measuring mass. Well, it turns out, remember that Newton's version, Kepler's third law. Again and again, we are using this to measure how much mass there is out there. And for example, in this case, we're going to use the orbit of the sun going around the galactic center. So remember for that, and what is that formula? Period square is 4 pi square over the big M, the total mass, times the universal constant of gravity, and then times the semi-major axis, or the average radius of the orbit cubed, right? So this would be A, the average radius, and the speed is actually the 2 pi r, the circumference of that circle, divided by the period. So some playing with these formulae will actually give you a nice formula for the mass enclosed. So we have mass enclosed in basically sun's orbit. And in case you're curious, the formula, so this is basically the radius of the orbit of the sun around the galactic center. This is given by, we have the radius, and then we have the rotational speed squared divided by capital G. And that, right, we put all these values that we were able to measure, like how long it takes for that for a full rotation of the sun around the galactic center, which is 230 million years. And we have the same major axis, right, A, or radius, okay, radius, let's use the same notation, okay, and that is 28,000 light years. Actually, we're going to convert these years into seconds and these light years into meters, and then use this formula, and guess what you're going to get? This many kilograms, and then convert into solar masses. So you get this many solar masses that are enclosed in this orbit, 10 to the 10. So that's actually 8.7 times 10 to the 10. So 87 billion suns exist out there. And that's about it for now.